Okay, welcome everyone. Welcome, you Feng. All right, so we're gonna give it just a few minutes, people to come in. So you just do my usual introductory stuff for those joining for the first time. Let me make this bigger. Okay, so if you aren't already on our Discord, here it is. Take a picture of this if you want. And you can also find our stuff in all these places. You can view this talk via YouTube, LinkedIn, eventually our learning site. Take a look at that. That's emerging. And if you want to work with us, even better. Best way is to start hanging out with us on something of mutual interest. This is how we've grown our team. All right, and anyone interested in systems, distributed systems, programming languages, operating systems, databases, please let us know. We're looking for folks like that. And still no one brave enough to present classic papers, but here are some. And other ways, get involved. If you're a startup, you can present. And if you want to donate, we'll be very, very happy. Okay, just a reminder, today we're going to kick off our new format, 1 hour total. So the talk will be 30 minutes, 40 minutes or so, the rest Q&A. And then after that, we'll move over to Discord for any additional discussion. All right, so we'll try this out. maybe this will make it easier for people to squeeze it into their day. We're also thinking people won't have to extend their slide presentations that they might have used for a conference. Okay, and without further ado, Feng is going to talk about her work. As usual, Joe has his nice selection of Art Deco. And you can find her work in these places. We'll send this out so you can get the details or take a picture. And these are the papers she'll be covering. All right, and we can take questions and comments from all three of these places. And heads up about next week. All right, have another great talk. Okay, take it away, Feng.
Great. Yeah, thank you. Thanks, Alex, for the introduction. Can everybody see my screen? Yeah, okay, I think so. I'd like to thank the Neuro-Symbolic Wednesday for giving me this opportunity to present my work. And since today is April Fool's Day, I thought it will be an especially appropriate time to talk about reliable large language model systems. AI is now everywhere. We are seeing large language model-based systems integrated into writing tools, search, coding assistants, healthcare, and decision support systems. Companies like OpenAI, Google, Meta, and Cloud, and others are all pushing these systems into real products that people use every day. Of course, the fact that AI is everywhere also means its failures are everywhere. This slide shows a bunch of examples which we are already seeing in practice. On one side, models can misuse data and generate harmful and fabricated content. And on the other side, they are actually making bad decisions. A model may not just say something wrong, but actually choose an unsafe action or behave in a way that is clearly misaligned with user intent. Just to get an idea of where we are, we can look at this figure where I show a different task performance. And the main pattern here is that the models tend to do much better on memorization-focused tasks compared to those that is reasoning and decision-making focused tasks. However, although frontier models are very impressive here, they're still much less reliable when we do need robust decision-making. And this is what I mean by the model solutions gap. There's still a substantial gap between the current model performance and the level of the reliability you would want for a real-time decision-making. And this gap is where I think the important research should work on. And this is also the motivation for the neuro-symbolic approaches that I will discuss later today. So let me briefly frame the main messages of this talk. Everybody is very excited about large language models, and for good reason, but what remains difficult is that these models still cannot reliably reason, plan, and support decision-making. One possible remedy here is just to use neuro-symbolic assistance. We can combine the flexibility of large language models with the reliability, structure, and verifiability of symbolic tools. For example, we can use probabilistic tools or solvers. So the goal here is not to replace large language models, but to make full use of their capacities and complement them, and so that eventually the overall system will be more trustworthy. So in this talk, I will present two of my recent works. The first is BERT. The problem here is that large language models cannot reliably reason, and so that they cannot produce accurate probability estimations. The research question we try to tackle here is how we can use probabilistic tools, especially Bayesian networks, to actually enable models to have better decision-making capacities. The second word is VeriCoT, which will be presented in this year's iClear. The problem here is chain of thought reasoning is very popular and it's very useful as well, but it could be very flawed and it's not faithful. So the question here is whether we can use softwares to verify chain of thought faithfulness and eventually enable the model to generate better chain of thoughts. Without further ado, I will go to the first paper I will present. Current large language models are good at a lot of things, especially tasks related to grammar and knowledge. However, they struggle with decision-making, especially they don't work well with partial information and they cannot reason constantly. One important reason here is that they cannot output reliable probability estimations for decisions. So in this paper, we'll use language models and we will make full use of its capacity to actually generate a Bayesian network, estimate the conditional probability tables, and then with that, we can actually produce reliable probability estimations. Let's take a look at a concrete example. We're going to build two charging stations. However, the two chosen locations should be on opposite side of the river and they should not be too close to each other. And this leaves us with two choices. We could choose either A1, B2 or A2, B1. We want to show that the language models cannot support a decision here. By the way, partial information is known about each location. If we directly ask the model to give you a decision here by rank A1, B2 and A2, B1, one possible answer is in one round is the model says that you should choose A2, B1. And then I rerun it in another sample. The model actually said that you should choose A1, B2. So the message here is that the large language models cannot produce a consistent binary ranking here. And this decision actually requires granular probabilities for each location. Not just a single end-to-end preference. We need to kind of estimate uncertain properties of each location and then compose these estimates into a final choice. And more generally, I think decision-making under uncertainty requires a structured representation of the probabilities over the relevant variables and outcomes. And a Bayesian network is definitely one of the most natural way here to represent the structure. Although language models cannot support a decision here, the good thing about a large language model is that it can actually help you build a Bayesian network by identifying the relevant variables and the dependency structures among them. They can even help with computing the CPTs. I will briefly go through exactly what we think the language models are good at. First, the language models are good at generating real-world factors to construct a Bayesian network for decision-making. Okay, before I go any further, let me mention one small caveat here. I'll actually use a simplified Bayesian network here to just model whether we should build a charging station at a certain location. The idea here is just to decompose the overall problem so that each candidate location is evaluated independently using just the same Bayesian network. But the final decision in the original task is actually over a pairs, right? So there are constraints across these pairs. So in the for decision-making problem, I will still need to have a higher level kind of a compositional layer to aggregate the local probabilities into a final choice. But from this slide and onward, I will just focus only on the first step here, which is the key point of this paper, using a large language model assistant Bayesian network to produce more accurate probabilities just for individual decisions. Great. Then let's just take a look at the language models behaviors. In order to decide whether to build a charging station at a certain location, the large language models actually knows what we should consider. For example, you should consider the EV ownership and many other factors. This lets us estimate each site independently in a structured way. So basically, given any scenario, we'll just ask a language model to come up with the possible factors. Large language models can also ground the factor values because it can identify key information from incomplete textual descriptions And then with that, given any condition, which is the partial information about a location, we can always use the language model to help of entailment to actually map the condition to the instantiated factors. For example, here, A1, it says that it's close to a high traffic errors and there's no nearby charging station. I will then give an overview of the paper. We propose BERT, a trustworthy Bayesian inference framework for abduction deduction for large language models. Given a scenario, we will use abduction to come up with the factors. We'll then use these factors as the variables in the Bayesian network, and then further calculate the conditional probability table. And during inference, given any condition grounding the scenario, we will use entailment to map the condition to the instantiated factors. We will then inject all the information back to the Bayesian network and eventually use deduction to derive the decision with reliable probabilities. And then I will go through the details of the framework. The first step is to build the Bayesian network. Given any scenario, we have an individual decision here, whether we should build a charging station at a certain at a certain location. We will use the large language model's help to determine the factors and their values. And then we need to calculate the conditional probability table. Basically, we need to calculate all complete information probabilities here. However, language model alone cannot actually output accurate and consistent complete information probabilities. So let's first take a look at the characteristics of the complete information probability here. We actually will adopt a derived formula where it kind of decomposes the complete information probabilities into individual probabilities over factor values. So under conditional independent factor assumptions and a uniform price, we can actually have this constraint for any CPT values. However, none of these probabilities is known or can be directly estimated by a language model. But the good thing here is that we can actually use coarse estimations from large language models of both and design a constraint optimization approach to actually learn the CPT values here. First, language models are really good at deciding which outcome is better supported by a factor value. So here, given a single factor value high EV ownership, it should better support the outcome that a charging station should be built here. And then we can use this as additional information, and this will be the direction of each individual probabilities. The second thing the language models are really good at is they are really relatively good at providing coarse probabilities when they given complete context. So here it is, instead of asking the model to give you a numerical probability, we ask it to rank whether this building a charging station here, given all this complete information, is very likely, likely, somewhat likely, or like very unlikely, somewhat unlikely, or unlikely. And then we will adopt a link-log scale theory to actually transfer the verbalized probability back to a number. And this way, we can also have some like large language model guided complete information probabilities estimate. And then we have our constraint optimization problem, where we will use each individual probability as the parameter to be learned. We will try to minimize the difference between the large language model verbalized coarse probabilities under complete information and BERT estimated probabilities. We also need to we also have a bunch of constraints here. The derived formula must be satisfied so that we have this connection between the complete information probability and the individual probabilities. Also, we need to make sure that each individual probability actually preserves the correct outcome direction. Once with these, we can actually do a constraint optimization, and then once each individual probability is learned, the CPT is actually fully determined. Since we already have the assignment of the conditional probability tables, we just need to calculate the observations. And this will be done with the language model entailment, where we kind of have a condition and then map the conditions to the instantiated factors. And here we can see that once we map the conditions to the factors, we use the learned CPT to calculate the final probability for each of the conditions. And with BERT, we can actually output multiple reliable probabilities at the same time. And let's go back to the original example. Here, we now have the probability, individual probability for each of the location. And even without any like abstractions, compositional layer on top to make this decision, we can still get an answer here that we should choose A2, B1. And this is also the correct answer. BERT enable us to actually see the nuance difference in the probabilities. Given the time, I will just give a brief rundown of the other experiment, and then I will talk about the first experiment in detail. So with BERT, it can help you generate much better probability estimations for decision-making. It also can give you better binary decision-making performance. And since we can output probabilities, we know the answer distribution, and we can use the distribution information to train better, smaller models. And also, since we know the factors for one decision, we also we have this entailment. We know which factors are not implied, and also we know the individual factor probabilities. We can ask effective follow-up questions to actually help the user make a better decision. Great. I will talk about the first and the most important experiment in this paper. The challenging here is that in many decision-making problems, it is really hard to get a four-goal probability distribution. So instead of asking whether the model matches the goal distribution exactly, we'll use a preference-based pairwise evaluation. Given a scenario, we'll sample two different conditions. For each condition independently, the model outputs a probability distribution over the two possible decision outcomes. And then we ask a relative question, does the model assign a higher probability to the goal outcome under the condition that better supports it? And this is essentially a three-label classification where we have three possible outcomes. The first is condition 1 better support the goal outcome. The second is condition 2 better support the goal outcome. The third is condition 1 and condition 2 are kind of indifferent. We show here that a BERT with a worse model actually can perform way better in terms of accurate probability estimations. We see a 30% improvement. By the way, we use an F1 score here. And we further show that even with the EC setup, where the model will be given two conditions at the same time to do a direct comparison, where we don't actually ask the model to output any probabilities, we still see that the BERT actually performs better than the EC setup. To sum up, in this paper, we kind of use large language models as estimators to abstract word modeling, and we construct this Bayesian network with the language model's help, and we could also estimate CPT with their assistance. And this gives us interpretable and reliable probability estimations for decision making. BERT is only one example of using large language model to support decisions. They cannot reliably make on their own, and there could be a lot of broader extensions. For example, first, we can extend it into complex reasoning scenarios where the decision is not only individual, but also a multi-hop or compositional. And this will be extremely helpful for scientific discovery as well, because the scientific discovery is kind of a natural setup here for if we are thinking about hypothesis generation or evaluation, it's naturally a graph. We could also think from a more fundamental set that we can extend this framework to causal networks, and we can thus enable interventional reasoning. Okay, great. This is basically what I would like to talk about for the first paper. And now I will talk about the second paper, VeriCoT. Chain-level prompting has enabled large language model to perform impressively multi-step reasoning. However, there's no built-in mechanism to actually verify the accuracy of the chain-of-thought reasoning. Chain-of-thought that are not always consistent with final answers, and here are some evidence I get from the papers that this is actually a very recent paper. Only 2.3% of the chain-of-thought reasoning here actually causally drive the final prediction. And this is an evidence from an old paper that truncating the reasoning chain changed the final answer for like smaller than 10% of the time on ARC and OpenBook QA. Also, a lot of times we see very fluent reasoning chains that lead to the correct answer, although the intermediate steps are logically flawed. And here's one example. We can see that the step 2 here is wrong just because Charlie was born in 2005 and this year is 2023, so Charlie should be 18. It shouldn't be at most 15. So in this paper, we'll use large language models to actually do the translation and formalize them into the first order logic. And then we'll enable the SMT solver to verify the logical consistencies. And this will help us diagnose flawed reasoning and also produce reliable training signals. Let me give you a task formalization here. We work on document QA. So given a document, an optional user background or conversational history, and a user question, a model will generate a chain of thought. And here, the chain of thought also includes the final answer. Our goal here is to verify if each step of the chain of thought is logically valid, and if not, we will identify the precise source of failure for this particular step. And then I will give you an overview of the VeriCoT algorithm. We will build an iteratively constructed SMT program for a chain of thought. The first step is given any chain of thought, we will decompose it into separate reasoning steps, and then we will translate each reasoning step into first order logic. We use SMT here. And then at each step, we will use the C3 software to run checks on the newly generated logic. And here we know that this step cannot be logically derived because it is the first step. So we kind of need to include additional premise to help ground this step. We extract the information from the question that it is exactly describing what is going on in the first step. We translate that premise into the first order logic as well, and then put it in front of the current step's logic. And with this, the step can be grounded. And next, I will go through the step 2 in more detail. The first step is we will use language model to translate the natural language statement into first order logic. The sentence we need to translate here is Charlie is at most 18 years old in 2023, and we already have some vocabularies we used in the first step. So in order to avoid introducing new duplicated formalizations, we will just ask the model to translate based on the previous vocabulary. However, here, this sentence will be untranslatable just because we haven't defined year and age. So we will detect formalization issues. If any part of the statement is not formalized, we will call the schema generation prompt to actually define the missing component. And these will be the new declarations added to the vocabulary. With the new vocabulary, we will be able to translate this sentence. This process will be repeated at most 3 times, and if the statement still cannot be properly translated, we will log a non-translatable error for this step. And then we need to do the checks. We'll conduct 2 different checks on the translation of one step. The first is a consistency check. The consistency check will only fail if there's contradictions between this step and the previous step. But obviously here we don't see any contradictions. So we will pass the consistency check for the step. However, if we do see there's contradictions between steps, then we will log a contradiction error message for that particular step because it won't pass the consistency check. The second check we will conduct is the entailment check. We will negate the reasoning steps and then trying to see if the solvers can output the onset for this part. But here we will see that it won't pass the onset check just because the step is not grounded. There's not enough information to make sure this step must be true. When the onset check fails, this means that the previous steps alone cannot be able to ground the current step. Then we will add external supporting premise from available natural language resources. And there are 3 different kinds of resources. First is document, the second is question, and the third is common sense. And common sense are just kind of general word knowledge or common sense assumptions that is not explicitly stated in the context. So let's go back to this second step again. We have already translated into first order logic, and we need additional promise to ground the step. The first additional promise we have here is someone's age is at most the current year minus their birth year. And the second statement we need to have here is just to ground the year. So this year is 2023. With these 2 statements, we now have kind of built the connection between the first step and second step, and we will be able to pass the check. So what we will do here is first step generating a supporting premise from available natural language resources, and then translate it also into first order logic, and then redo the onset checks. So here I have already added the new premise, and then we need to do this check again. With the new premise, this time, we will pass the entailment check. But if there will be scenarios, even we added a new premise, it still fails the onset check. And then we will log an ungrounded error message for this step, which means the step is not actually sufficiently supported by the document or previous steps. We will also use the language model as a judge to actually evaluate on the premise generated by the language model. And we want to see if it is actually factual or acceptable common sense. And now let's basically go through the second step, and then let's just take a look at the third step here. This step, it also cannot be grounded from the previous step. It needs additional information, the premise. And we will extract the premise from the document to support the step. We will have a premise generated by the language model, and then we translate it into first order logic. With this step, with this premise, the third step can be grounded. And then we will tackle the fourth step. The first step here is actually supported by the previous step, so we don't actually need additional premise. It will automatically pass all the checks. Great. So basically, with the VeriCoT verification algorithm, we would like to check if a chain of thought is actually valid. So if the chain of thought is valid, we will eventually get a bunch of first-order logic premise, and we will see that each step is grounded and it's logically valid. And if it is invalid, VeriCoT will actually identify the error reasons for each step. It could either be ungrounded just because we don't have enough sufficient premise to actually entail the step, or it could be contradiction. Existing statement actually contradict with this current step, or there could be some untranslatable. There could be some translation issues that the statement cannot be translated into the first order logic subset that is supported by VeriCoT. And then I will talk about the experiment. We test on 3 different data sets, especially we are particularly interested in the high-stake domains. We test on legal bio questions. We also test on kind of a tool task of just the proofs. Now let me show the main verification result for VeriCoT. Across all three datasets, VeriCoT achieved the strongest verification performance, outperforming all the other baselines. Here, the explanation refiner is it's a paper that is a award winner of EMLP 2024, I think. It shows it kind of used Isabelle as the way to verify explanations for entailment tasks. Direct SMT baseline is just we generate the SMT without our designed translation algorithm. VeriCoT without premise is we don't introduce any premise to ground the steps. So in that case, if the step is factual, we just do the set checks. If the step is an inference step, then we do both set and unset checks. The metric here is VCAR. This measures the percentage of the examples where two things are both true. First, the final answer is correct, and second, the chain of thought is formally verifiable. So this is a kind of intentionally stricter metrics that standard answer accuracy. It is not enough for the model to land down the right answer by luck. We also wanted the reasons itself to be checkable by the verifier. And this is not a final task accuracy. It's just about verification quality. I also want to mention about the things VeriCoT can translate and cannot. The good thing about VeriCoT is we introduce quantifiers. This helps us a lot, especially when it comes to document QA. For example, like legal document, there are a lot of like generic rules. Well, but we still think there are a lot of things that cannot be supported by the current translation algorithm. Just for example, like probabilistic statement or temporal statement, or any higher order logic. We now show that VeriCoT is used for not only for checking reasoning, but also for improving it. The basic idea here is that once we verify the chain of thought, the verification output can be feedback to the model for self-reflection. In this figure, we compare the distribution outcomes before and after self-reflection. And what we see here is that after self-reflection, the proportion of valid chain of thought increases, while the proportion of ungrounded ones decrease noticeably. The contradiction categories are also goes down slightly, but the untranslatable cases stay roughly the same. We show that VeriCoT is useful not only at inference time, but also as the training signal. The core idea is simple. We will use VeriCoT verification signals to filter distilled chain of thought. So the only logically consistent chain of thought will be used for fine-tuning. Important thing that here is that we are assuming we don't know the gold task label. So if we do supervised fine-tuning on randomly distilled chain of thought here, we get some improvement. But if we fine-tune on verified chain of thought, performance improve a lot, especially the final task accuracy. And then we actually add DPO on top of the SFT. DPO stands for direct preference optimization, where we choose two data point, and we ask the model to learn to prefer one over the other. And then if we do this DPO on top of SFT, we see a great improvement for verification quality, which as expected. So better verification signals lead to better training data, which in turn kind of lead to better reasoning and better downstream performance. To sum up, VeriCoT is a neuro-symbolic chain of thought verification algorithm via logical consistency checks. We could also see there are a lot of broader extensions for VeriCoT. For example, we should think about including richer logic. We can extend VeriCoT to more complex domains that require richer reasoning structures, for example, like temporal procedural reasoning. We can also use VeriCoT to gather larger scale synthetic data. One thing that I like about VeriCoT is that it can even teach models to detect the decorative reasoning steps that appear plausible but are not logically useful. The other thing I think it's very useful is we could include the probabilistic aspect. We can incorporate probabilistic programs to measure the degree of logical support between the step and the uncertainty through the verification chains. Great. So basically, that's the two paper I covered today. The common trait here is that it is about neuro-symbolic collaboration, where language model will be the neural part. We make full use of the language model capacities. For example, in BERT, we use the language model to generate the Bayesian network, and then calculate the conditional probability table. And in VeriCoT, we use the large language model to do the translations, and we also use it to generate premise. And then we have the symbolic part. In BERT, the symbolic part is actually the probabilistic tools. It's the Bayesian network itself. We will just use the Bayesian network to compute the reliable probabilities. And for VeriCoT, the symbolic part is just SMT solver. The C3 solver will conduct the checks to instruct us about the errors in each of the chain of thought steps. With BERT, we have more reliable decision making when large language models cannot reliably do it on their own. And with VeriCoT, we have effective verification tools for assessing the language model's output. This can also serve as synthetic data for further training of language models. So as I just mentioned, for both methods, it can be beneficial for both inference and training. With BERT, we could also use this distribution as another like a distributional-wise signal to fine-tune smaller models. And with VeriCoT, it can benefit both inference and training as well. Yeah, great. That's basically what I would like to talk about today. And thank you for listening to talk, and open to any questions and discussions.
Thank you. Great stuff. All right, we have a bunch of questions. I'll read them out. 1 second. I find the beginning. Okay. In BERT, is there a human in the loop at any stage?
When we design the framework, there's human in the loop. But when we do this like inference, and the framework itself doesn't have any human in the loop.
All right. Comment from Michael Whitbrock.
But it's an automatic, like it's a fully automatic framework, and it can be parallelized for any condition. So it's also very efficient.
Excellent, good. Comment from Michael Whitbrock about how late it is in some parts of the world, or sorry, early. This is from New Zealand. We have our
wow.
So yes, Discord. So this highlights the value if you can jump on Discord after this. I think it'd be great for some might be able to interact in any discourse. All right. How accurate is the conversion to first order logic?
Yeah. Let me show you. I think I have a slide for that. We conduct a human. We actually conduct a human analysis, and we see that the translation quality is like always over 80%, and also kind of varies across different tasks. Because like BioAsk is about bio questions, and there are a lot of like different difficult terms in bio questions. But for Sarah, which is a kind of more structured document of legal documents, we do see a better translation quality. So in general, the translation quality is pretty high because we spend a lot of time trying to develop this translation algorithm.
Yeah, just to mention here, this is for those of you who haven't tried doing it, translating natural language into the formal logic is very, very tricky. Like not even just, there are many many issues you would imagine, like ambiguity and so on, but even what is the right what is the right ordering of quantifiers and so on. Much more difficult than it sounds.
Yeah, I agree. Yeah.
Okay, how does VeriCoT generate and verify the supporting premises to ensure each chain of thought reasoning step is logically valid and grounded in context or common sense knowledge?
Yeah, that's a great question. We will actually use the language model's help. So here, we'll input all the informations from the verification, the software to the model, and then to a large language model and ask it to, and then saying that the step cannot pass the software's check, and we believe there's missing premise, and can you generate premise that support the step? We also have some few short examples. Then the model itself will generate the statement. And the other thing is we will check whether the statement itself, the translated first order logic, passed the verification, the set check. We want to make sure the new admitted premise is not messing up with the current translation.
Okay, great. Not sure if you missed the statements that cannot be translated, but would fuzzy logic be an option?
Yes, it could be an option, but I think for this step of the project now, we just want to make sure everything is very controlled and clear. So like we have like really clear signals for each of the steps. But in the future, we should consider all this like a different kind of logic, for example, fuzzy logic. I will see it as a future step.
Okay, I think just to give two possible translations of this question. One could be that you assign a probability to potentially different meanings of the sentence. In other words, your semantic parsing may not have understood the sentence, so it's fuzzy. Even in its meaning. Is that something you consider?
Yeah, that's also the reason why I kind of mentioned the probabilistic program. It's like one way is we could try to measure or capture the ambiguity in the sentence, where we could kind of have a probability, different translations with probabilities. Although the other thing about probability program is we could actually measure or capture the probability or the uncertainties between different steps. Like even chain of thought itself is not always deterministic. There could be scenarios where you're kind of thinking as a tree, like a tree of thought, where you could have possible different paths.
Okay, great. Since probabilistic statements cannot be translated in VeriCoT, were there any such examples in the data set? How are they dealt with for the experiment? Also, which data sets have these for future work?
Yeah, I think for legal bench and proofwriter, they are deterministic. Actually, I think all the data set we choose here are deterministic because we work on all those like high stake domains where we value the accuracy and we don't want ambiguities in the questions or answers at all. And that's the reason why we choose these three data sets. But I would imagine that if we kind of generalize to a more general decision-making scenarios for document QA, like a more kind of a user-based card, like if you are going to do some shopping and you have some constraint on that, then I would imagine that we will have, we need to use probabilistic things there.
Okay. Is the first order logic representation a limiting factor on expressiveness?
Yes, yes and no. Yes, just because as you also mentioned that it's really difficult for a language model to translate from natural language to any kind of logic. So if we kind of constrain it into a simpler logic, it's easier for the language model to do the translation. I would imagine if we use a more advanced model, for example, if we use the most recent cloud, I would say it should be able to generalize or translate better to have more expressibility in terms of the logic it can translate. Yeah, because I do see that the current models should be able to do a better job for translation.
All right. How can VeriCoT's verification feedback be used practically to improve reasoning accuracy and trust during inference and model fine-tuning, especially in domains like biomedical or legal reasoning?
Yes. So basically, as we show that the VeriCoT will give you signals for the failures, why each step fails. It could be ungrounded just because we don't have enough premise to support the. Oh, sorry, we don't have enough premise to support that step, or it is contradiction previous steps. All these can be first be kind of gathered all together as a message to the model and ask it to self-reflect on its own uh, errors, and that's where we do the self-reflection. We give all the informations from the verification algorithm back to the model and ask it to rewrite the chain of thought. The other thing is we can use the verification algorithm to distill data. We only admit the data point where it passed the verification. And the other thing we're not doing here, but I think could be promising, is we just use this verification algorithm as the way for reinforcement learning training, like a JRP or all this kind of style training, where we just use that as a verification signal. We can reward based on the quality of the verification. For example, if all the steps pass the verification, we give the highest score, and if only one step passed, we just give like a lower score. And we can also give different scores based on different weights on different kind of errors.
Okay, great. I'm curious what natural corpus VeriCoT has been tried on to probe the limits of fidelity of the auto-formalization. Regulatory?
I see. I think that's also like go back to we'll have to go back to the translation problem of language models. Like it's very hard for the translation, so we're not actually working on any like a really natural language form context. But with that being said, the chain of thought itself is natural language because we didn't do any interventions or constraint on how the language model generate the original chain of thought. So basically, we just work on the original chain of thought, and that's the natural language part. But for the question itself, the document, they are like well-formed language like this. It's still natural language, I would say, like a fuzzy natural language.
All right. Related, is there a background knowledge base that is used? And if there were, how would the cost of inference grow with that background knowledge?
Yeah, because we work on document QA, so we have a background, but just specifically for this particular point, data point. So we don't actually have like a large database. You can assume in this setup we have a clean data point where we have the assigned document for this particular question. And if you're talking about, for example, we have to retrieve the right document from a large database, I think it's out of scope for this problem, but it's kind of a separate problem.
Okay. Can the same pipeline of VeriCoT be applied to verify chunk retrieval steps on, for example, RAG systems?
The RAG systems, if I interpret it as the result of the RAG systems, then yes, because we can see whether this step is grounded in the document or not. And if we are talking about more general web search agents where it could search multiple steps, I think it should also be beneficial because we can always translate each of the searching step into the first order logic to see if they are logically valid. But the thing here is we do see, at least from my perspective, I see in a lot of web agent behaviors that you see a lot of like back propagation, you see a lot of cases where you kind of reflect and then go through another certain trace. So I am not sure if we should do this verification during the process of an agent searching for a do retrieval. We probably can just do it on the final retrieval trace.
Okay. After the verification using VeriCoT, what kind of cases are uncaught or missed? Is there a pattern in those cases which can be linked to any limitations of the work?
Yes. I think we do see one pattern in legal bench where if the legal bench question is a numerical question where it have like a very long chain of thought trace about numerical steps, sometimes the step will fail for ungrounded issues just because we kind of sometimes the data in the chain of thought, the model will do some rounding, but it's not obvious that the language model, when it generates premise, will realize we need an actual premise for grounding. So a lot of the times there, if you don't have a premise for grounding, like rounding, saying that if a number is larger than 0.5, then it should be up to 1, for example, then we will see some translation failures. But we already fixed that in our prompt by explicitly add this premise to the premise generation prompt.
Okay, and that's the most common type of thing?
Yeah, that's the most common type of thing for legal batch. And for document, for proofwriter, I don't think we see any like very common issues, but we do see that the more complicated the chain of thought is, and then the less likely it will pass the check just because the model that generate the chain of thought could have a lot of like logical gaps, and they might jump from one thought to another very quickly without actually explaining anything. And in this case, we will have to rely on our premise generation to fill the gap about generating all the possible, like all the like intermediate premise, but that will be very difficult. So that's also one pattern I see in proofwriter.
Okay, great. I had some questions, but we had a ton of questions from our audience. It's always great. So maybe another time you will talk. But I'll just comment that there are not too many works addressing probabilistic inference in LM. So I really appreciate that you did that. It's relatively unexplored, I think, because I think most folks are still just basic logic, getting a basic logic right is still completely open, as you showed. And you could regard the probabilistic extension of that as even harder. So, okay, just a comment also that we saw a bunch of people just joined Discord, so welcome everyone. The Discord channel is Neuro-Symbolic Wednesdays. So, and that's where the party happens. So if you have more questions we didn't get to for you, throw them there. And you at some point, if you can jump on, that'd be great.
Yeah, I already joined the Discord.
Oh, awesome. Okay, so thank you so much. Great talk, great work. Hope to continue seeing what you're doing.
Yeah, we try to extensions on both works. Yeah.
All right. Keep up the good work. And thanks everyone for joining. We'll see you next time.
Thank you.